Every year, over 90 million tons of chemical fertilizers are produced worldwide, without which half of the planet's population would simply have nothing to eat. But how exactly are these granules, which nourish life on Earth, created? In the depths of giant underground mines, in reactors with a pressure of 5,000 pounds per square inch, and at a temperature of almost 900 degrees Fahrenheit, chemists transform gas, rock, and salt into something that becomes bread on our table. But behind this technological perfection lies a secret. A process that changed the course of history and at the same time put humanity at a risk that few people suspect. Watch until the end, and you will understand why these granules can be both a salvation and a threat. The production of chemical fertilizers is one of the most important industrial processes in the world, as it provides the key nutrients, nitrogen, phosphorus, and potassium, to support global food production. It is a complex, energy-intensive, and high-tech chain of chemical transformations that begins with the extraction of raw materials and ends with a granulated or liquid final product. Potash fertilizers, the source of which is potassium, are almost entirely made from natural deposits of potash salts, usually potassium chloride. The process does not require complex chemical reactions, as in the case of nitrogen or phosphorus, but is mostly a process of physical beneficiation. Potash ore is mined from underground deposits. The ore consists mainly of potassium chloride, table salt, and other minerals. After mining, the ore is crushed, and then the potash salt is separated from unwanted components. The main beneficiation methods include flotation and crystallization. Flotation involves mixing the crushed ore with water and special chemical reagents. The reagents selectively adhere to the particles of potassium chloride, and then the mixture is passed through a chamber where air is introduced. The potassium particles stick to the air bubbles and float to the surface, forming a foam that is collected. Crystallization, on the other hand, uses the difference in the solubility of salts with a change in temperature. The ore is dissolved in hot water, and upon cooling, potassium chloride crystallizes first, separating from other salts. The purified potassium chloride is dried and granulated to obtain a commercial product. If it is necessary to produce potassium sulfate, a fertilizer that is better suited for some crops sensitive to chlorine, potassium chloride can be chemically processed, for example, with sulfuric acid, although this method is more expensive. The production of nitrogen fertilizers, the largest group, is based on the synthesis of ammonia, which is a fundamental building block. This synthesis is almost entirely carried out by an industrial method known as the Haber Bosch process. Nitrogen is obtained from ordinary air, and hydrogen is most often obtained from natural gas by steam reforming. The first step is the preparation of hydrogen. Methane reacts with superheated steam at a temperature of 1,400 to 1,600 degrees Fahrenheit and relatively high pressure, which leads to the formation of synthesis gas, a mixture of hydrogen and carbon monoxide. Then the carbon monoxide reacts with additional steam in a conversion reactor to produce even more hydrogen, converting carbon monoxide to carbon dioxide. After purification, which includes the removal of carbon dioxide and residual impurities, a high purity mixture of nitrogen and hydrogen in a 1:3 ratio is obtained. The Haber Bosch process itself takes place in high-strength reactors, where the purified gases of nitrogen and hydrogen are passed over a catalyst, usually iron-based, at a temperature that typically ranges from 750 to 950 degrees Fahrenheit and at extremely high pressure, often from 2,000 to 5,000 pounds per square inch. The reaction, which shifts towards the formation of ammonia under high pressure, is exothermic. The ammonia that is formed is separated from the unreacted gases by cooling to a liquid state. The unreacted gases are returned to the process, which ensures high production efficiency. Liquid ammonia is either the final product or an intermediate raw material for obtaining other nitrogen fertilizers. For example, For the production of urea, liquid ammonia and carbon dioxide react under pressure and temperature, first forming ammonium carbamate, which is then dehydrated to the final urea. For the production of ammonium nitrate, ammonia is first oxidized to nitric acid, and then the nitric acid is neutralized with additional ammonia. The final products are often granulated or pressed into pellets for ease of storage and application on agricultural land. Phosphate fertilizers supply plants with phosphorus and usually begin with the mining of phosphate rock, which contains phosphorus in an insoluble form. To make phosphorus available to plants, the rock must be chemically processed, most often with sulfuric acid. The production of sulfuric acid, which is critically important, occurs by burning sulfur or pyrite to form sulfur dioxide, which is then oxidized to sulfur trioxide, and finally absorbed by water. The processing of phosphate rock occurs by the wet process. The crushed phosphate ore is treated with sulfuric acid in reactors. The main reaction converts insoluble calcium phosphate into water-soluble phosphoric acid, and an insoluble byproduct, calcium sulfate, known as gypsum. The gypsum is filtered and removed. ENG6. The resulting phosphoric acid, which has a low concentration, can be used to produce so-called single superphosphate by its direct interaction with additional phosphate rock. However, more often the acid is concentrated by evaporating water and then neutralized with ammonia. Neutralization leads to the formation of highly concentrated fertilizers, such as monoammonium phosphate or diammonium phosphate, which are among the most common phosphate compounds. Many modern fertilizers are complex, meaning they contain all three primary elements: nitrogen, phosphorus, and potassium. They are produced by mixing intermediate products in precisely defined proportions to achieve the desired formula. The mixing can be physical, meaning a simple mixing of granules of different fertilizers, or chemical, where all components are contained in one granule. Complex fertilizers are often subjected to granulation. At the initial stage, there is a precise dosing of all necessary components to achieve the desired nutrient formula. Dry powdered materials and often liquid components are fed into a mixer. Here, the raw material is thoroughly homogenized to ensure that each future granule will contain an identical balance of nutrients. This ensures uniform application, as the farmer can be sure that every square foot of the field will receive the required amount of nitrogen, phosphorus, and potassium. The mixed raw material enters the main apparatus, the granulator. In industry, two main types are common: drum granulators and pan granulators. A drum granulator is a large rotating cylinder installed at an angle. A binding agent, often water or steam, is added to the raw material, as well as heat. The rotation of the drum and the stickiness caused by moisture and heat cause the small particles of raw material to stick together and roll into granules. As the particles are coated with new layers of material, the granules increase in size. The heat supplied to the granulator, often in the range of 180 to 250 degrees Fahrenheit, not only promotes chemical reactions, but also evaporates part of the moisture, making the newly formed granules stronger. The granules coming out of the granulator are moist and not strong enough. To achieve the required hardness, they are sent to a large rotating dryer. There, hot air reduces the moisture content, usually to less than 1% by weight. This is a critical step, as excessive moisture will cause the fertilizer to cake during storage. After drying, the granules are cooled in a special cooler. Rapid cooling strengthens the granule structure and prepares it for final processing. The cooled granules pass through a system of screens that separates the perfectly sized granules from those that are too small or too large. Granules that are too large can be mechanically crushed. Particles that are too small and dust are returned to the mixing stage in the granulator, where they serve as seeds for the formation of new granules. This recycling cycle is the key to the high efficiency of the process and minimization of waste. The granules are calibrated to a precise range, for example, from 1/16 to 1/8 of an inch in diameter, which ensures their suitability for modern sewing equipment. One of the first in the United States to receive a patent for an artificial ice-making apparatus was Dr. John Gorey of Florida. His main goal was not to cool drinks, but to create cold air to cool rooms for patients suffering from yellow fever, as well as to produce ice for hospitals. This happened in 1851, and today it is estimated that about 2.5 million commercial ice makers operate in the United States of America, used in various fields, from restaurants to large industrial productions. Let's see how it all happens. At a large food-grade ice production plant, which can produce from 50 to 100 tons of ice per day, the process of turning ordinary water into transparent, perfect ice looks like a consistent, high-tech conveyor. Here is a step-by-step visualization of how it happens, using the example of tube ice production, which is most often used for packaging in bags. Water, often from the city water supply, but sometimes from wells, is pumped into a large water storage tank. This is the starting point. From there, the water begins its journey through a system of mechanical filters to remove large impurities, rust, and sand. Next, it goes to a workshop where carbon filters are installed to remove chlorine and organic substances that affect the taste, and, most importantly, reverse osmosis or deionization systems. The systems forcibly push the water through semi-permeable membranes, removing salts and minerals, which are the main cause of cloudy ice. Purified water is the key to transparency. The purified water with minimal impurity content is collected in a special clean water working tank ready to be fed into the ice maker. Clean water from the working tank is fed by a powerful pump to the upper part of the ice maker. This is a tall cylindrical chamber with dozens or hundreds of vertical tubes. The water is pumped into a distribution system above the tubes and begins to flow continuously in a thin layer down the inner surface of these vertical tubes. The walls of the tubes are intensely cooled from the outside by a refrigerant, for example, ammonia or freon, to temperatures well below freezing. But since the water is constantly moving, only pure water freezes on the walls. All air bubbles and the last mineral impurities are washed away by the flowing water and return to the lower circulation tank. During a certain cycle, which usually lasts from 15 to 30 minutes, long, thick cylinders of clean, transparent ice form inside the tubes. When the ice reaches the required thickness, the valves in the ice maker system switch sharply. The refrigerant is turned off, and instead, hot gas from the compressor is supplied to the outer walls of the tubes. This thermal shock instantly melts the thinnest layer of water between the ice and the tube wall. The huge ice tubes fall under the force of gravity from the machine down onto a cutter. The knife cuts them into even, standard pieces that we are used to seeing in bags. From there, the ice is transferred to a belt conveyor. The ice falls into a large insulated storage bunker, the ice storage bin, where the temperature is maintained slightly below freezing. The bunker is not a freezer, as the ice must be free-flowing and not stick together. From the bunker, the ice is automatically dosed onto packaging machines, where it is weighed, sealed in bags, usually of 7, 10, or 20 pounds for the consumer market, and transported to pallets for further shipment. Thus, the quality, transparency, and safety of the ice are ensured precisely by the combination of thorough filtration in the first stage and constant circulation of water during freezing in the second stage. Industrial ice makers come in different types, depending on what form of ice the city needs. The most common are machines for producing block, tube, plate, and flake ice. We have already looked at tube ice. This is one of the most popular types for drinks and the food industry. But there are others. Block ice. These are classic massive blocks weighing from 50 to 300 pounds or even more. Although it is now less common than before, it is still used when very long-term cooling is needed. For example, for large batches of fish. For its production, purified water is poured into large metal molds, which are then immersed in a huge tank filled with a cold brine solution at a temperature of about 23 degrees Fahrenheit. freezing such a massive block can take from 24 to 48 hours. And there are also flake ice and plate ice. These types are used mainly for cooling products or in concrete mixers. Flake ice, these are thin, dry, flat crystals up to 1/10 of an inch thick. It is produced by freezing water on the outer or inner surface of a rotating drum, from where it is constantly scraped off. Plate ice, with a thickness of about 1/2 inch, is obtained by freezing water on vertical cooling plates and periodically separating it with hot gas or warm water. A typical large industrial ice maker, especially of the tube or flake type, can have a capacity of 40 to 80 tons of ice per day. At the same time, there are individual installations with a capacity of 500 tons of ice and more per 24 hours to serve large enterprises, for example, fish processing plants or large logistics hubs. Although modern machines create small granules or tubes of ice, traditional block ice is produced in molds weighing up to 300 pounds, with the 150-pound size being considered the largest that one person can comfortably handle. Studies have shown that in household appliances that have an automatic ice maker, up to 3/4 of the energy used to make ice is spent not on actually freezing the water, but on heaters that briefly turn on to separate the ice from the mold tray and drop it into the storage compartment. This problem is less relevant for large industrial machines that use other, often thermal or mechanical methods of ice collection. The total annual electricity consumption of all commercial ice makers in the United States is estimated at about 13.5 terawatt-hours per year. This is a huge figure that underscores the importance of the industry for the energy sector. Industrial ice production is also a significant consumer of water. For example, water cooling a compressor, although more energy efficient, can require up to 22 gallons of water for every 100 pounds of ice produced. However, the use of evaporative condensers allows for reducing this ratio to less than 1/2 ton of water for every ton of ice, thanks to recirculation. Before the invention of industrial refrigeration units, in the 19th century, the natural ice trade was a huge and influential industry in the United States. Ice, cut into massive blocks from the frozen lakes of New England, was delivered by sea and rail all the way to the southern states, the Caribbean, and even India. The traders of this natural ice, known as the Ice Kings, initially actively fought against the spread of artificial ice, claiming it was unhygienic. The main argument that destroyed the position of the Ice Kings was the pollution of lakes and rivers. Natural ice was literally a frozen piece of contaminated water. Although freezing kills some bacteria, it does not destroy all pathogens, and more importantly, concentrates mineral and organic impurities. In contrast, manufacturers of artificial ice used science and technology as their main marketing tool. At the factories, artificial ice was made from water that was first filtered and then purified, as we discussed. The water for artificial ice was often even cleaner than that which flowed in the city taps. The most convincing argument was the transparency of the factory ice. As we have already mentioned, the process of rapid freezing of moving water, as in tube ice, removes air and minerals, making the ice crystal clear. Imagine, you throw away an old washing machine, not even suspecting that it could live another life. But where does your appliance actually end up after it's been taken away at a discount or for free? Is it really recycled, or just buried under a layer of earth? Behind every seemingly dead machine stands a whole industry of destruction, separation, and material revival. Giant shredders, magnetic separators, eddy current fields that separate aluminum from steel with centimeter precision. And at the end of the video, you'll learn something that's not mentioned in any trade-in advertisement. What really happens to your old appliance after it disappears from your home? Many major brands and electronic stores offer a trade-in program or free removal of old appliances when you buy a new one. For example, in the United States, companies like Whirlpool, LG, and Samsung have such programs, and in Europe, initiatives like the Waste Electrical and Electronic Equipment Directive are in place. The terms can vary, Some companies simply take the appliance, while others offer a discount on a new purchase. Whirlpool in the United States might offer a $50 to $100 discount on a new appliance for an old washing machine. LG and Samsung sometimes offer $100 or $200 as part of promotional programs. In Europe, some programs allow you to get up to 10% off a new appliance. But more often than not, the discounts aren't very large. Most companies view this as an environmental initiative rather than a way to attract customers. In many cities, there are electronic waste collection centers where citizens can bring old washing machines themselves. Often these centers work in cooperation with municipalities or private companies. In some countries, including Germany, the United Kingdom, and the United States, there are municipal services that provide collection services for large electrical appliances. For example, in New York City, you can order a free pickup through the NYC Safe Disposal program. Some companies are involved in secondary metal recycling, so they may buy the washing machine or take it for free. They send the appliance for dismantling, where they extract metal, electronics, and plastic. First, the machines are sorted into categories: working, partially working, and non-working. Working ones can be repaired and resold, while those beyond repair go to dismantling. Dismantling begins with removing the outer panels, doors, and drum. The motors, electronics, wires, and pumps are separated, as they can be reused or melted down. Metals are sorted separately: stainless steel, aluminum, and copper. Plastic parts are also sent for secondary recycling. This process can be done both manually and with the help of special automated lines that shred the casing and separate the materials using magnets and air separators. Automated lines for recycling washing machines consist of several stages, each responsible for separating different materials. First, the machines are fed onto a conveyor belt, where they are shredded by powerful rotary shredders. The blades of these shredders are capable of tearing metal and plastic casings into fragments ranging from 3 to 10 centimeters in size. After shredding, the materials pass through magnetic separators. They attract ferromagnetic metals, such as steel and cast iron, separating them from the rest of the components. Next, an eddy current separator comes into play, which uses a magnetic field to push out non-ferrous metals, including aluminum and copper. Plastic and light materials are separated using air separators. Powerful streams of air lift the light particles up, sending them into special containers, while the heavier ones remain on the conveyor. At the end of the sorting line, the remaining materials are additionally checked with optical scanners that analyze their composition and direct them to the appropriate sections for further processing or disposal. After the materials have been sorted using air separators and optical scanners, they go to separate processing lines. Plastic, metal, glass, and other materials are processed for further use or recycling. The remaining metals, such as steel parts, are sent to metallurgical enterprises for remelting and further use in the production of new goods. Magnetic separators effectively extract iron and steel, which are sent for remelting. Plastic parts are shredded and pressed into briquettes. These briquettes can be sent to specialized enterprises for the production of new plastic products, or for use as secondary raw materials for new technical devices. If the washing machine has glass elements, for example, doors or windows, they are thoroughly cleaned of any contaminants and can be melted down to produce new glass. The remaining materials that are not recyclable, for example, certain types of rubber or mixtures of materials, are sent for disposal or burial at specialized landfills. Such sorting and recycling lines significantly reduce the amount of waste that ends up in landfills and help return raw materials to the economic cycle. In some cases, for particularly complex materials, additional technologies are used, such as thermal decomposition or chemical treatment. They are used for materials that cannot be simply separated by mechanical methods, or that require additional processing to prevent contamination or harmful emissions. For example, some plastic components that contain a combination of materials such as plastic with metal inserts or rubber parts. Such materials may not be subject to simple sorting and require special processing to separate the components. Often, rubber elements, especially with the addition of chemical compounds, are not effectively recyclable due to their complex structure. For such materials, thermal decomposition or other chemical processes may be used to break them down into simpler components that can be reused or disposed of. In some cases, when an appliance contains toxic substances, for example, mercury in old relays, batteries, or lighting devices, such materials must be processed by special methods. This can be a chemical process that neutralizes harmful components or isolates them for further safe disposal. Polyurethane or polyester materials, which are often found in wire insulation or in various components of household appliances, can be subjected to thermal decomposition to separate them into simpler components that can be recycled. In cases where washing machines or other appliances contain complex composite materials that have several layers of different substances, for example, plastic with metal or fibrous components, special processing may be required to separate these layers and for the subsequent recycling of each of them. In general, such technologies are used to ensure maximum efficiency of disposal and to reduce the negative impact on the environment, as improperly processed materials can lead to pollution or the leakage of dangerous substances. Every year, over 20 million tons of glass are recycled worldwide. But have you ever wondered what actually happens to the bottle you just tossed into the recycling bin? It's about to embark on a journey through fire of over 1,500 degrees Celsius, magnetic fields, and air currents, where even a tiny impurity can ruin everything. Glass is broken, sorted, melted, and then it's born again. Sometimes as the very same bottle. But that's not the most interesting part. Because at the end of this video, you'll learn the secret that every transparent wall hides, and it will change your perception of trash forever. So, how does a glass product get a new life? The recycling of bottles begins with the collection of used glass. In many cities and countries, there is a system of separate waste collection, which contributes to effective recycling. In many cities in different countries, special containers are installed for collecting glass, separate from containers for plastic, paper, and organic waste. This helps to prevent the mixing of glass with other materials, which simplifies the subsequent recycling process. But some countries or companies implement a system of glass collection points, where people can turn in used bottles and receive a reward for it. This stimulates the population to participate in the collection and return of glass bottles for recycling. In many countries of the former USSR, this collection is carried out by unprotected and marginalized segments of the population. But in EU countries, it's a daily practice for everyone to turn in used containers and receive, for example, a discount on their supermarket bill. The collected glass is sent to recycling plants, where the main processing begins. After the glass bottles are collected in containers, or through collection points, they are transported to special sorting centers for further processing. The waste is collected by special garbage trucks that periodically empty the collected glass from the containers and transport it to sorting centers or directly to recycling plants. This is usually done on a large scale for more efficient transportation. Sorting by color is extremely important because different colors of glass are used for different products. Mixed colors can degrade the quality of new products. The bottles are sorted automatically. For this, special optical scanners are used that automatically recognize the color of the glass and sort it into clear, green, and brown. This is important because different types of glass require separate processing. The sorting machines are equipped with special sensors that identify the color of the glass using light sensors. Whole bottles or pieces of glass move on a conveyor belt, and the machines illuminate them with a lamp or laser. The light reflected from the glass is analyzed by sensors. The system determines the color of the glass about which a signal was received and sends a note about it to the controller. After color identification, each piece of glass is sent to the appropriate section, either by a stream of air or mechanically removed from the conveyor. The glass is divided into separate streams, which greatly simplifies further melting and use in new products. After sorting by color, the glass passes through magnets and air streams that remove metal elements, such as caps, as well as other impurities, paper labels, or plastic residues. Powerful magnets are installed on the conveyor line, which capture all metal impurities, including iron caps. And electromagnetic separators are used to remove aluminum caps and foil elements. Pneumatic removal is used to remove plastic and label residues from the conveyor. A powerful stream of air blows away the parts unnecessary for further glass recycling. And of course, the glass also undergoes wet cleaning in special washing systems, as many of these bottles will be used after recycling to create containers for food products. Just imagine, we throw away bottles as they are, and don't think about how much effort is needed for their further recycling. And compared to other materials, glass does not wear out or degrade during use. After sorting, the glass is crushed into a state of cullet, which is the raw material for the production of new glass products. For this, special machines are used to crush glass bottles into small pieces, which facilitates further processing. Crushers come in different types, but most are based on a mill with two parts, one of which is stationary, and the other is moving. The glass is simply ground during the friction of one part of the unit against the other. They can be jaw, cone, roller crushers, hammer mills. The glass is loaded into the crushing machine through a hopper or a conveyor belt. In the crusher, the material is processed by mechanical elements that reduce it to the required size. Some crushers may have several stages of crushing to achieve uniformity of particle size. At this stage, any residual impurities that were not removed during sorting can be further removed. After crushing, the cullet is sifted to remove particles that are too large, or conversely, too small. This is done to obtain a uniform mixture of cullet at the output, which is suitable for melting. New bottles or jars are most often melted from the fine cullet. It's a bit unsettling that they make new dishes from trash, isn't it? But powerful processing and high temperatures leave no chance for the glass to carry even a speck of something unpleasant into the finished product. After crushing, the cullet is cleaned of contaminants and undergoes additional processing before being sent to the melting furnaces with the help of magnetic separation. This process is used to remove any residual metals that may have remained after sorting. This is important, as even small metal impurities can negatively affect the glass melting process. Next, special technologies are used to remove residual organics, such as paper labels, adhesives, or other materials. This ensures that the cullet is completely clean before melting begins. Then the glass crumb is sent to vibrating screening machines, where it passes through screens of different sizes to be separated into fractions. Different coarseness is used for different products. The entire process at this stage is automated, and the machines are equipped with control and management systems. The use of specialized machines minimizes the risk of injury to workers during the processing of glass bottles, as the entire process is carried out in a protected environment. After cleaning, the cullet is sent to recycling plants, where it is transformed into a new glass mass. At the plant, the cullet is loaded into special furnaces, where it is melted at a temperature of 2,800 to 3,000 degrees Fahrenheit. The glass becomes liquid and ready for the formation of new products. Adding cullet to the melting process allows for reducing energy consumption, as recycled glass melts at a lower temperature than raw material. Adding new raw material, sometimes a certain amount of new raw material, sand, soda ash, limestone, is added to the melting process to maintain the chemical composition and quality of the glass. This helps to ensure the strength and transparency of new products. After the glass turns into a liquid mass, it is used for the production of new glass products. The liquid glass is directed into molds that create various products, for example, new glass bottles, jars, vases, or other glass containers. The bad part of the recycled glass is then used as a filler in concrete. This increases aesthetic appeal, strength, and improves thermal insulation. At large factories, this process is fully automated and can include high-precision molds to ensure the required quality and thickness of the glass. After forming, the glass products pass through special cooling systems, where the temperature is gradually lowered. This is important to prevent the formation of cracks and to ensure the mechanical strength of the products. After forming, the new glass products undergo strict quality control to ensure they meet safety and strength standards. For this, optical and mechanical tests are conducted. Special systems check the products for defects, such as air bubbles, cracks, or incorrect shape. If a product does not meet the standards, it is sent for reprocessing. Then the products are also tested for mechanical strength, especially when it comes to glass bottles that must withstand pressure and other loads during use. After all stages are completed, the new glass products are packaged and transported to the market for further use. At large factories, the packaging process is also automated. The glass products are grouped, packed in cardboard boxes or on pallets for convenient transportation. The new products are sent to warehouses or directly to customers, beverage, food, and other goods manufacturers, where they will be used again, and the glass recycling cycle can begin anew. After all, this is a profitable and useful business. Glass recycling plays a significant role in reducing greenhouse gas emissions and water pollutants. By using recovered glass material to make jars and containers, humanity is able to minimize waste and reduce its carbon footprint. In addition, to make glass from scratch, a method of raw material extraction must be used, which does not have the best effect on the environment. Glass recycling has significant environmental benefits as it is energy efficient. The use of recycled glass, cullet, allows for reducing energy consumption for the production of new products, as melting cullet requires a lower temperature than melting raw material. Researchers on this issue indicate a 3% reduction in energy consumption. This also reduces the amount of waste in landfills. Glass is non-biodegradable in natural conditions and can remain in the environment for thousands of years, so its recycling is an important contribution to environmental preservation. Undoubtedly, recycling contributes to the conservation of natural resources. Glass recycling allows for reducing the use of natural raw materials, such as sand, soda ash, and limestone, which helps to preserve natural resources for future generations. Every year, over 4 billion tons of concrete are produced worldwide, more than any other man-made material. But few people know that it can be made significantly stronger, more environmentally friendly, and even cheaper, with the help of dust from ancient volcanoes. Volcanic ash, a natural gift that can replace up to half of the cement, reducing carbon emissions by hundreds of pounds for every ton. How exactly does ash that once fell from the sky turn into concrete that can last for centuries? Watch until the end, because at the end, you'll learn a secret that could change the perception of construction. Depending on the type of concrete and specific requirements, volcanic ash can replace from 10% to 50% of Portland cement by weight. On average, many projects use a replacement of about 20 or 30%. Our journey begins in quarries, where we extract high-quality volcanic ash. This natural material, left after ancient volcanic eruptions, is a key ingredient in our concrete. First, large excavators load the raw volcanic ash into dump trucks, which deliver it to our processing plant. Here, the ash undergoes primary processing. It is crushed to the desired particle size and sifted to remove any large impurities. This stage is extremely important for ensuring the uniformity and quality of the final product. We use specialized crushers and screens that allow us to obtain a fine powder, which provides optimal reactivity in the concrete mixture. After crushing, the ash is stored in large silos, ready for use. At this stage, we also conduct strict quality control, taking ash samples for analysis in our laboratory. We check its chemical composition, specific surface area, and density to ensure it meets our high standards. Each batch of ash must pass a series of tests before being approved for further processing. This allows us to guarantee the stable quality of our concrete. After preparation, the volcanic ash is transported to a central mixer, where it is combined with other key ingredients: cement, water, and sand and gravel. The mixing process is carefully controlled by a computer system to achieve the perfect consistency. Here, volcanic ash acts as a pozzolanic additive, which improves the properties of the concrete, making it stronger and more durable. The ratio of ingredients is determined by our engineers and depends on the specific requirements for the concrete. For example, for concrete that will be used in aggressive environments, we add a larger amount of volcanic ash to increase its resistance to sulfates and other chemicals. Water is supplied through dispensers that accurately measure its quantity to ensure the optimal water-cement ratio. This ratio is critically important for the strength and workability of the concrete. Additionally, we may use various chemical admixtures, such as plasticizers or hardening accelerators, to modify the properties of the concrete. These additives allow us to adapt the concrete to different construction conditions. For example, to ensure rapid setting in cold weather, or to increase its fluidity for easy placement. Cement production is an extremely energy-intensive process. The use of volcanic ash, which is a natural material and does not require intensive thermal processing, significantly reduces the overall energy consumption in concrete production. This can lead to an energy reduction of 20% compared to traditional concrete. After thorough mixing, the liquid concrete is fed to the forming lines. Depending on the final product, we use different forming methods: casting in molds, vibropressing, or extrusion. These machines are automated and provide high precision and production speed. For example, for the production of concrete blocks, we use vibropresses, which compact the concrete mixture under high pressure and vibration, creating strong and uniform blocks. For the production of slabs, we use molds into which the concrete is poured, and then it is compacted using vibrating tables. These molds can be of different sizes and configurations, allowing us to produce a wide range of concrete products, from small landscape design elements to large building structures. An important part of this stage is also reinforcement, if it is necessary for certain products. Steel reinforcement is inserted into the molds before the concrete is poured, which significantly increases the strength and load-bearing capacity of the final product. The entire process is controlled by operators who monitor the operation of the equipment and the quality of the finished products. Volcanic ash significantly improves the resistance of concrete to sulfate attacks, chloride corrosion, and alkali-silica reaction. Sulfate resistance can increase by up to 50%, and the reduction in chloride permeability by up to 70%. This makes it ideal for marine structures, roads with high salt use, and wastewater treatment plants. After forming, the concrete products are moved to curing chambers. This is a critical stage where the concrete gains its final strength. In these chambers, optimal temperature and humidity are maintained, which promotes the hydration of cement and volcanic ash. The curing process can last from several hours to several days, depending on the type of concrete and strength requirements. After curing, each product undergoes strict quality control. Our specialists check its dimensions, shape, and surface for defects. Samples are also taken for testing for compressive strength, bending strength, and frost resistance in our laboratory. We adhere to the highest quality standards to ensure that every product manufactured at our plant meets or exceeds our customers' expectations. Each concrete sample is subjected to a series of tests to ensure that it can withstand the declared loads and operating conditions. This includes tests for tensile strength, water impermeability, and resistance to aggressive environments. We also conduct non-destructive testing using ultrasonic and X-ray methods to detect hidden defects. After successfully passing quality control, the finished concrete products are transported to warehouses, where they are stored until shipment. The production of 1 ton of Portland cement generates approximately 2,000 pounds of carbon. By replacing 25% of the cement with volcanic ash, we can reduce carbon emissions from concrete production by 250 pounds for every ton of cement produced, or by 60 pounds for every cubic yard of concrete. Concrete with volcanic ash is used in a wide range of construction projects: bridges, roads, dams, tunnels, where high strength and durability are required. It is estimated that 20 to 30% of infrastructure projects in regions with available volcanic ash could effectively use this material. Foundations, walls, floor slabs, where strength and environmental friendliness are important. For example, in geothermal projects, where resistance to high temperatures and aggressive fluids is required. Not all volcanic ash is the same. Its properties vary significantly depending on the source and geological history. The ash can come from different igneous rocks, such as rhyolite, andesite, and basalt. Each type has a different chemical composition, meaning the content of silica, aluminum, and iron, which affects its pozzolanic activity and color. Finer ash usually has a larger specific surface area, which provides a faster and more effective pozzolanic reaction. However, particles that are too fine can increase the water demand, so a balance is needed. The quality of volcanic ash largely depends on the content of the amorphous phase. It is this phase that is the most reactive. Crystalline components are less active. We carefully analyze this indicator in our laboratory. In addition to functional advantages, concrete with volcanic ash can offer interesting aesthetic possibilities. Depending on the chemical composition of the source, volcanic ash can give concrete different shades of gray, brown, or even black. This can eliminate the need for painting, or allow for the creation of unique aesthetic effects. For example, ash with a high iron content can produce warmer tones. Thanks to the fine particles of ash, the surface of the concrete can be smoother and more uniform, which is valued in architectural concrete and decorative elements. Every year, humanity creates energy that on one hand saves cities, and on the other, hides an incredible story of transformations. One average reactor produces 1,000 megawatts and requires only 27 tons of enriched uranium per year, the weight of 3 school buses. But to get these 27 tons, you have to mine and process over 100,000 tons of ore. In this video, we will follow the path from a noisy mine and acid vats to supersonic centrifuges, furnaces, and tiny fuel pellets. Every step is chemistry, giant machines, and unexpected risks that you are almost never told about. Stay until the end, and I will reveal one secret to you that will change your perception of atomic energy. An average American nuclear reactor has a capacity of about 1,000 megawatts. For it to operate for 1 year, it needs approximately 27 tons of enriched uranium fuel. 27 tons is the weight of about 3 school buses. And now let's compare. To produce the same amount of electricity, a coal-fired power plant needs to burn over 3 million tons of coal. That's over 10 million barrels of oil. Nuclear fuel is the highest form of energy concentration that humanity has ever created. But to get these 27 tons of fuel, you need to start with a much, much larger amount of raw material. The chain of transformations is simply staggering. To produce those same 27 tons of enriched uranium fuel, you need to start with 215 tons of uranium concentrate. And to get those 215 tons of concentrate, you need to mine and process over 100,000 tons of uranium ore. Imagine a giant mountain of stone, the size of a multi-story building, which ultimately turns into a volume of fuel that fits in one truck. This shows how dispersed uranium is in nature and how complex the process of its concentration is. It all begins in the roaring chaos of a uranium mine. Imagine a deep shaft or a giant open-pit quarry, where huge machines with a deafening roar bite into the rock. The air here is thick with dust, and every stone that is brought to the surface looks absolutely ordinary, just a gray, dull granite or sandstone. The uranium here is invisible. It is dispersed in the rock in the form of tiny microscopic inclusions, and its concentration is incredibly low, often less than 1%. This means that to get 1 pound of uranium, you need to mine and process hundreds or even thousands of pounds of barren rock. Dump trucks, loaded to the brim, take this ore to a nearby processing plant that hums. The first stop is the primary crusher. This is a giant steel maw that, with a deafening crunch, crushes large stone blocks into pieces the size of a fist. Then, this crushed stone goes by conveyor to a huge mill. A giant rotating drum, filled with steel balls, resembles an industrial washing machine for stones. Here, in a continuous roar, the ore is ground into the finest, grey sand, almost dust. And now the real chemistry begins, a process called leaching. This grey sand is mixed with water, forming a thick pulp, and pumped into huge vats, the size of a small house. A powerful chemical solvent is added to these vats, most often sulfuric acid. This acid, like a hungry predator, begins to eat the uranium, pulling it out of the solid rock and turning it into a liquid, dissolved state. This process lasts for many hours, while the entire mixture is continuously stirred. As a result, we get two things. On one hand, tons of wet, now unnecessary sand, so-called tailings, which are toxic waste, and on the other, a murky, greenish-yellow liquid containing our precious uranium. This liquid needs to be cleaned and concentrated. It is passed through a series of columns filled with special ion exchange resins. Imagine this as a high-tech water filter. The resins, like a magnet, pull out only the uranium ions from the solution, letting everything else pass by. Then these resins are washed with another solution, which washes the concentrated uranium off them. And so, finally, our final product is precipitated from this clean, saturated liquid. By adding ammonia or hydrogen peroxide, the uranium is forced to fall out of the solution in the form of a bright yellow, thick precipitate. This precipitate is filtered, dried in furnaces, and at the output, we get the same famous yellow cake, a heavy, radioactive, mustard-like powder. This is the uranium oxide concentrate, the first step on the long path to clean energy. The next step is purification to an absolute, almost unearthly purity. The yellow cake is sent to a special plant, where it is dissolved and, with the help of complex chemical processes, such as solvent extraction, all impurities are removed from it. The goal is to obtain perfectly pure uranium dioxide. But here the main problem arises, which is at the heart of all nuclear energy. In this perfectly pure uranium, 99.3% is the stable, lazy isotope uranium-238, which cannot sustain a chain reaction. And only 0.7% is the energetic, unstable isotope uranium-235, which is our fuel. They are chemical twins, and it is impossible to separate them by chemistry. To make the reactor work, we need to increase the concentration of this energetic uranium-235 from 0.7% to 3 or 5%. To begin enrichment, the solid uranium must be converted into a gas. It is treated with hydrofluoric acid, turning it into uranium tetrafluoride, and then with fluorine to obtain uranium hexafluoride. This is a very corrosive and dangerous compound, which has a unique property. It becomes a gas at a temperature slightly above room temperature, and so this gas, packed in special containers, is sent to an enrichment plant. Imagine a giant, noisy workshop the size of several football fields, filled with thousands of identical, tall, metal column-like devices. These are gas centrifuges. Each of them is a high-tech top that rotates at supersonic speed, making tens of thousands of revolutions per minute. When our uranium gas is pumped inside, the magic of physics begins. The heavier gas molecules with uranium-238, under the action of centrifugal force, are pressed against the walls of the centrifuge, and the very slightly lighter molecules with uranium-235 remain closer to the center. This is a microscopic difference, but it is enough. Special tubes take the gas from the center, which now contains a little more uranium-235, and send it to the next centrifuge in the cascade. And the depleted gas from the walls is diverted to the side. To achieve the required concentration of 3 or 5%, the gas must pass through thousands of such centrifuges. This is an incredibly long and energy-intensive process. When we have finally obtained our uranium hexafluoride, enriched to the required level, it needs to be converted back into a solid material suitable for fuel. With the help of chemical reactions, it is turned into a black powder of uranium dioxide. But this is not just any powder. Each of its particles has a perfectly calibrated size and shape. Now the most interesting part begins, the creation of fuel pellets. This black, heavy powder is sent to a press. Imagine a high-precision pharmaceutical press, only instead of medicine, it stamps radioactive pellets. It compresses the powder with incredible force, turning it into small, dense, perfectly cylindrical granules, or pellets. They are still brittle, like chalk. To give them strength, they are sent to a furnace. But this is not an ordinary furnace. This is a high-temperature furnace, filled with hydrogen to prevent oxidation. There, at a temperature of over 3,000 degrees Fahrenheit, these pellets are baked for many hours. During this process, called sintering, the powder particles fuse together, and the pellet turns into an extremely hard, dense, ceramic-like substance. It becomes so strong that it can withstand the extreme temperatures and pressures inside a nuclear reactor. Each pellet after this undergoes laser control, which checks its dimensions with micron accuracy. The next step is assembly. These small black ceramic candies are carefully, one by one, loaded into long, thin tubes. These tubes, about 13 feet long, are not made of steel, but of a special zirconium alloy called zircaloy. This material is unique in that it is very strong, resistant to corrosion, and most importantly, almost transparent to neutrons, allowing the chain reaction to proceed without hindrance. When the tube is completely filled with pellets, it is filled with an inert gas, usually helium, to improve heat transfer, and hermetically sealed at both ends. Now, it is not just a tube with pellets, it is a fuel element. And the final stage is the creation of a fuel assembly. Several hundred such ready-made fuel elements, for example 17 by 17, which gives a total of 289 pieces, are assembled into one large square bundle. They are held together by special spacer grids. This ready-made assembly, which looks like a giant, high-tech quiver with arrows, is the final product. It weighs about half a ton and is ready for shipment to a nuclear power plant. And so, having passed an incredibly long and complex path from an ordinary stone through chemical transformations, supersonic rotation in centrifuges, infernal baking, and precise, almost clockwork assembly, this concentrated bundle of energy is born, ready to quietly and reliably produce millions of kilowatts of clean electricity for several years. Imagine this. In the heart of the ocean depths, or in the roar of an airplane turbine, there is a part that decides everything. A single shaft, capable of transmitting the power of 1,000 Ferraris, or withstanding speeds of over 10,000 revolutions per minute. But how is this steel axis, which can lift a space shuttle, born from an ordinary cold ingot? And what do a ship's propeller, the size of a 3-story building, and the precision of a jeweler, removing a few grams of metal, have in common? In this video, we will reveal the secret of creating giants, without which neither a ship nor an airplane can move. Watch until the end. A fact that will turn your understanding of the power of metal upside down awaits you. A shaft is a steel rod that transmits colossal power from the engine to the propeller. You can't just take any steel for it. Giant, perfectly clean steel ingots, each weighing tens or even hundreds of tons, are brought to the factory. This is not scrap. It is a special vacuum-degassed alloy from which almost all impurities have been removed. This massive cold cylinder is first sent to a furnace. But this is not a melting furnace. This is a giant heating chamber where, for many hours and sometimes days, the ingot is slowly and uniformly heated to a temperature of about 1,200 degrees Fahrenheit. It becomes dazzlingly yellow, plastic like clay, ready to meet the hammer. And so begins the most brutal and ancient art of metallurgists: forging. A giant crane picks up the red-hot ingot and places it under a hydraulic press hammer. This is a monster capable of dropping its top with a force of tens of thousands of tons, with a deafening, deep boom that makes the ground tremble. The hammer slowly but relentlessly descends onto the red-hot metal. These are not quick strikes. This is a slow, methodical squeezing. After each strike, a manipulator slightly turns the ingot. And so, strike after strike, hour after hour, the formless cylinder begins to stretch and take the shape of the future shaft. This process does not just change the shape, it does something incredible inside the metal. It compacts its crystalline structure and aligns all the grains of steel in one direction, along the axis of the shaft. It's like turning a scattered pile of straws into a tightly twisted rope. A shaft born in a forge will be many times stronger and more resistant to torsion than a simply cast one. After the forge, we have a rough, black, scale-covered blank that only vaguely resembles a shaft. It's time for the sculptor. It is secured in a giant lathe. Imagine a lathe half a football field long. The blank begins to rotate slowly, and a cutter of super hard alloy is brought to it. With a hiss and a screech, it begins to remove layer after layer, turning the black, uneven surface into a perfectly smooth and shiny one. A continuous ribbon of hot, bluish metal shavings, resembling a streamer, comes off the cutter. This process lasts for many days. Computer control ensures accuracy to the hundredths of a millimeter over the entire 30-meter length. Some shafts are made hollow to reduce weight. For this, a perfectly straight hole is drilled through its entire length. After final grinding, the surface of the shaft becomes as smooth as a mirror. Now that the spine is ready, it's time to create its heart, the propeller. This is a completely different story. A propeller has an extremely complex, aero or hydrodynamic shape that cannot be forged. Therefore, it is born from liquid fire, by casting. The main material for marine propellers is not steel, but a special bronze. It is slightly less strong, but it is not afraid of corrosion in salty seawater. First, engineers create a perfect computer model of the propeller. Then, based on this model, an exact full-scale copy is carved from wood or foam. This model is a true work of art. Next, this giant model, which can be as tall as a 3-story building, is buried in a huge pit filled with special molding sand. The sand is carefully compacted around the model, creating a perfect impression of its shape. Then the mold is disassembled, the model is removed, and we are left with a cavity inside the sandstone that exactly repeats the shape of the future propeller. This is our casting mold. Meanwhile, in a giant induction furnace, tons of bronze are being melted. It turns into a liquid, dazzling gold, boiling at a temperature of 1,800 degrees. A huge ladle brings this river of molten sun to our mold. And the foundry workers, dressed in silvery fire-resistant suits, slowly and carefully, through special channels, begin to pour the metal into the sand mold. This is a tense and dangerous moment. The metal must fill every smallest curve of the mold, leaving no air bubbles. After pouring, a long cooling process begins, which can last for weeks. When the metal has finally solidified, the moment of birth arrives. With a roar and clouds of dust, the sand mold is broken, and our propeller is revealed to the world. It is still ugly, black, with a rough surface. It is sent for processing. First, the remnants of metal from the gating system are cut off, and then it enters the maw of a giant 5-axis milling machine. A huge milling cutter, controlled by a computer, for hours, layer by layer, removes the excess metal from the blades, giving them a perfectly precise, calculated aerohydrodynamic shape. But even after the machine, the surface is not perfect. It's time for manual labor. A whole team of workers with grinding machines, like an army of ants, for hours polishes each blade, bringing its surface to a mirror shine. Any unevenness on the surface of the propeller creates turbulence, which reduces its efficiency and causes destructive cavitation. And the final, most important test for both the shaft and the propeller is balancing. They are installed on a special stand and spun. Sensors detect the slightest vibration caused by imbalance. If there is even the slightest deviation, literally a few grams on a multi-ton part, it is eliminated by drilling tiny holes or removing a thin layer of metal. And only when this steel spine and bronze heart are perfectly balanced and fitted to each other are they ready to go to the port to be connected and begin their long service, silently and invisibly rotating in the dark to move giant ships across the oceans or lift airplanes into the sky. The engine of such a container ship can have a power of over 100,000 horsepower. Imagine the power of 1,000 Ferrari sports cars concentrated in one place. And all this colossal energy is transmitted through a single shaft to a single propeller. The torque on this shaft is so huge that if a lever were attached to it, it could easily lift an entire space shuttle. After final processing, the runout of the shaft over its entire length should not exceed a few hundredths of a millimeter. This is less than the thickness of a human hair. Imagine a perfectly straight line the length of a basketball court. Well, the real shaft does not deviate from this line by more than this microscopic amount, and the balancing of the propeller is generally a jeweler's work. On a 100-ton propeller, an imbalance of a few tens of grams is considered unacceptable. It's like finding and removing 1 grain of sand from the surface of a car. The turbine shaft in a modern jet engine, like the General Electric GE90 on a Boeing 777, is not just a rod. Its length is only a few meters, but it transmits incredible power. And the main thing is the speed of rotation. If a marine propeller makes about 100 revolutions per minute, then the high-pressure turbine shaft in a jet engine rotates at a speed of over 10,000 revolutions per minute. At such speeds, the slightest imbalance turns into a destructive force. Therefore, aviation shafts and turbine discs are balanced with an accuracy of fractions of a gram.